Whenever you talk about nuclear or radioactive chemistry, you definitely have to talk about half-life. Because radioactive isotopes don't necessarily behave the way that we have, other things behave chemically. Because what happens is they decay at a rate based on its half-life. So if you have carbon-14 right here, and its half-life is 5,730 years. If you have 1 gram of this carbon-14, it will take 5,730 years approximately to get half a gram of that. Okay? Then you start with half a gram, and it will take another 5,730 years to get to a quarter of a gram. So you're constantly thinking about how long it takes to get to half of the previous state. And it doesn't necessarily react all at once. It's just like that. So if you want to consider this like 100% of something you have, at the first half-life, half of it will be gone. At the second half-life, it'll be down to 25%. At the third half-life, half of 25 is 12.5, so it would be there. And so on and so on. Okay? So if you start off with 5 kilograms of carbon-14, how long would it take it to go to 0.625 kilograms? You start off by just cutting things in half. So 5 kilograms goes to 2.5 kilograms. 2.5 kilograms goes to 1.25, and 1.25 goes to 0.625. This would be one half-life, so 5,730 years, another half-life, and another half-life. So to calculate that, you just take 5,730 times 3, and make sure you account for significant figures. There's only 2 of them there, and that's how you get your calculation here, okay? Now, I'm going to do this first. Radioactive isotopes can certainly be used in imaging. So if you've ever had a CT scan, MRI, PET scan, those types of things are imaging, but really PET scans and CT scans use more of the radioactive type of things. Also, radiation would obviously use radioactive isotopes. So a PET scan is known as positron emission topography, and it uses a variety of very short half-life types of radioisotopes to quickly give images, 3D images of organs, so you could actually sort of see that in all forms. CT scan is computed tomography, and this is monitored by a computer, just as you have up here. X-rays are targeted at an organ, and the uptake is monitored to give an image of that organ, so to give sort of slice images, if you will, of that organ. MRI is not using anything that's radioactive. CT scans are using X-rays, so I don't know if that's sort of on the verge sometimes, but MRI is not radioactive, but what this is actually doing is it's using very, very powerful magnets to monitor protons in a different organ, brain, whatever it may be, and that sort of gives you a signature that a computer puts together to give very, very detailed imaging. Okay. Whenever you also talk about radioisotopes, it's important to talk about fission and fusion. So fission is where a large atom is going to split into 2 or more atoms, and it releases energy with that process. So like we have in atomic bombs and things like that, uranium-235 can actually lead to a chain reaction where it subsequently splits into other things. So say if you have uranium-236, it's actually 235 is bombarded with a neutron first. Then it's sort of split into 2 things, and then those things can split into other things, and that's basically what you mean by a chain reaction. So it's constantly leading to the next reaction, the next reaction, the next reaction. Fusion is what takes place in stars, where two small nuclei combine and release even more energy than what you have in fission. But the problem is it requires very, 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 very high heat to make that process begin. And that's what's going to fuel the sun, stars, that type of thing. Okay? Thank you very much.